So hi everyone. So in the previous part, I told like that the course overview section of the digital IC design. Okay. So before the starting of the digital IC design, I will discuss the some basic point that thing we will need if we go forward in the course. Okay, especially for the MOS transistor construction. Okay, that's why I am telling basic thing. Okay. So I hope those people who have a background of EC, so definitely those people have must idea of the EDC. Okay, but those guys, the background is the double E and instrumentation. So that guys don't have an idea about that. Okay, but the basic thing here I will tell. So what the need for a course? Okay, actually now so many college the IT and IT allow the double E and instrumentation in MTech in the VLSI design, yeah, embedded system. Okay, so without loss of time I am starting. Okay, so firstly I will telling about the intrinsic semiconductor. Okay, intrinsic semiconductor means no doubt you already know. Right now all the semiconductor we use the silicon semiconductor, germanium we can also use, but mostly all the semiconductor means we use only the silicon semiconductor. Okay, so the the intrinsic semiconductor, it is a pure semiconductor. Okay, this is a pure semiconductor, you can tell. Means the what are the meaning of pure semiconductor? Means there is no doping is there, no doping is there. Okay, this is the pure semiconductor. I will tell later what are the meaning of the doping. Okay, so the intrinsic semiconductor is, it is the pure semiconductor and no doping is there. So the silicon, I am taking example silicon. The fourth group element, sorry, the fourth group element is the silicon. The silicon is a fourth group element. Okay, in the periodic table, this is the fourth group element. This is the carbon, silicon, and this is the germanium. Okay, so I am using the silicon. Silicon is a fourth group element, so that's why it have a four valence electron. Okay, this is the four valence electron. Okay, this is the four valence electron, and only the valence electron will be responsible to contribute in the bond formation. Okay, in the bond formation only the valence electron will go. Okay, so to silicon have a four electron, four valence electron. So just I am taking the example, inside the lattice there are so many, the silicon is there. I am taking one section. Okay, one smallest section. Okay, so, the silicon having a four valence electron. This is the one electron. This is the two electron. This is the three electron, and this is the four electron. Outside also will be silicon is there. One silicon, and I am taking this is the another silicon atom. Okay, and this is the silicon. So because of that, it have only the four valence electron is there. So four electron, it will make the covalent bond inside the lattice. This is the covalent bond and covalent bond. Okay, this of the bond structure. See, see. So you know already. I think at zero degree Kelvin, this semiconductor behaves as an insulator. Okay, this semiconductor behaves as an insulator. But if we increase the temperature, this semiconductor behaves as a, if we increase the temperature, this semiconductor it behaves as a the conductor. Okay, at 0 Kelvin it behaves as an insulator. You know, okay, at 0 Kelvin it is insulator. But if we increase the temperature, means this way I am giving the energy, then it will behave as a conductor. How? Means if we increase the temperature, in that case this electron so will break the covalent bond and it is free. So like that, and only the free electron is responsible for the current conduction. Okay, so the current conduction, for conduction only the free electron is responsible, only free electron is responsible. Okay, so if we increase the temperature, then the covalent bond will break and the electron will free. If electron will free, then it will behave as a conductor. So at room temperature, at room temperature means the 27 degree Celsius, yeah 300 Kelvin, 300 Kelvin. On that temperature, how many free electron? It observed like that only 10 to the power 12 free electron concentration is there per unit volume. Okay, per unit volume. But the density of the silicon atom is inside the semiconductor, that is the 10 to the power 22 atom per centimeter cube. Okay, per centimeter cube. Okay, so if we increase the temperature and we observe like that at 27 degrees Celsius, yeah 300 Kelvin, only 10 to the power 12 free electron is there, and only this free electron is responsible for current conduction. So this is not much electron. Okay, so that's why we go for another semiconductor. Because of that, this is the 10 to the power 12. This is the less amount of the electron. Of course, it will behave such a conductor, but not much. Okay, there are the less free electron concentration. That's why we go for the another the semiconductor. But before the going that, okay, see, in that the concentration of electron and hole will be same. Means if a electron will go, suppose, so this is the bond. Okay, if he break the bond, if electron go from this place, this place will be replaced as a hole. Okay, this place will be replaced as a hole. So this is the symbol of hole. Holes is nothing but it is the absence of electron. Holes is nothing but it is the absence. No need to worry about that. You should have a not much knowledge about it. Okay, but hole is the absence of electron. Okay, I am telling in the simple word. This is the absence of electron, hole. This is the definition of hole, absence of electron. Okay, so this is the symbol of hole and this is the symbol of electron. Okay, so in case of the intrinsic semiconductor, it observed like that the concentration of electron and hole will be same. The concentration of electron and hole will be same, and that is called the intrinsic semiconductor, Ni. Okay, Ni. The concentration of electron, I am telling N symbol, and for hole I am denoting I'm representing P. Okay, so the concentration of hole and electron will be same in case of intrinsic semiconductor. But here the concentration of electron is less. That's why we go for extrinsic semiconductor. Extrinsic semiconductor. So extrinsic semiconductor, it is doping semiconductor. How we can obtain that thing? By the help of doping. Doping means doping means by adding extra element, either by adding by adding extra element, either the fifth group या third group, either by adding extra element the fifth group या the third group. Okay, in the periodic table, third group. So by adding the extra element fifth group या third group, we add in the intrinsic semiconductor. In intrinsic semiconductor, okay, intrinsic semiconductor. Okay, this is the meaning of doping. Here I will dope. So the extrinsic semiconductor, it will be the two types. So what are the meaning of doping? I told here the meaning of doping is simple. Here I will add the extra by adding the extra element. Either it be fifth group element or third group element in the intrinsic semiconductor. So see, the extrinsic semiconductor is two types. Extrinsic semiconductor is the two types. So one is the n-type semiconductor and another is the p-type semiconductor. One is the n-type and another is the p-type semiconductor. Okay. Actually, in the course overview part, that thing I told wrong. So extrinsic semiconductor, there are the two type, n-type and p-type. In the course overview, I told the intrinsic is two type, n-type, p-type. So sorry for that. Okay. So extrinsic semiconductor are two types, n-type and p-type. Okay, so firstly I will discuss the n-type semiconductor. This is the n-type semiconductor. Okay, the n-type semiconductor. In case, so how we can get the n-type semiconductor? By doping fifth group element. Here I will dope the fifth group element. By doping means I already told. So by doping, the fifth group element, the group element in the intrinsic in the silicon semiconductor, yeah, intrinsic semiconductor in the silicon semiconductor. Okay, so the fifth group element is like that. The phosphorus and arsenic also element is there. I am telling this. This is the best. This is the most useful. The phosphorus and arsenic. So this is the fifth group element. If this is the fifth group element, definitely it have a five valence electron. If the five valence electron is there, that electron will be the contribute in the bond formation. So I am taking this is the phosphorus element. Okay, it have a five valence electron is there. Okay, and I doped this in inside the silicon semiconductor. So here is the silicon semiconductor. Silicon is there. Because of the silicon only the four valence electron is there. This is the silicon. So the bond look like that. So the bond look like this is the bond, and this is the covalent bond, and this is the covalent bond, and this is the covalent bond. See, this one electron is left. Because of that, the fifth group element have a valence electron 5, but silicon semiconductor only 4 valence electron. So 4 it go for bond formation, and one electron is left. Okay, no problem. At 0 Kelvin, it behaves as an insulator. Okay, it behaves as an insulator. But if we increase the some temperature, then inside the lattice, of course, if we increase the some temperature, then this electron will be free. If this electron will be free, then it will be responsible for the current conduction. Okay, that thing not happen in the intrinsic. So this electron is right now not free, but if we increase the some temperature, this electron will be free. Okay, so at 0 Kelvin insulator, and if we increase the temperature, it behaves as a conductor. Okay, so it observed like that at room temperature. At room temperature means 27 degrees Celsius, the concentration of, here I dope the phosphorus atom. Na? So this atom is called the donor atom. This atom is called the donor atom. Nd I am writing here for representation, for representing purpose. Okay. So at room temperature 27 degrees Celsius, it observed like that the concentration of the electron, all the doped electron, actually in the EDC part is there. I am not going inside. So all the donor atom will be ionized, and it observed like that the concentration like that 10 to the power 15 per centimeter cube means once. So the concentration in increase, if you see like that, in case of the intrinsic only 10 to the power 12 is there, but in case of the extrinsic semiconductor, this concentration, donor atom concentration increases 10 to the power 15. So it will behave as a more conductive. Okay. So this is the n-type semiconductor. Okay. See, the donor atom, so this is the nd. So in case of the n-type semiconductor, in case of n-type semiconductor, I am telling this point you should remember. Okay, this is the important point. In case of the n-type semiconductor, electron is the majority carrier concentration, the donor atom. Okay, this is the donor atom. This is I am writing here the donor means what we donate, no, actually p. So it will extra one electron, due to that it is the donor atom, and an nd, and for n for electron. So this is the donor atom. Okay, and in case of the n-type semiconductor, the donor atom means electron will be the majority carrier. This thing you should remember. Okay, this is the majority carrier, and majority carrier, and the whole concentration, this is the whole concentration. Okay, this is the whole, and this is the electron. Okay, so electron will be the majority carrier, but whole is the minority carrier. You should remember that point. Okay, you should remember that thing. So in case of the n-type semiconductor, electron will be majority carrier, and whole will be the minority carrier. But you can ask, so one thing I am also telling. Okay, the representation of the n-type semiconductor is like that. This thing we will use in the most uh, construction for n-type semiconductor. Because of that, it will donate the one electron to the lattice. So so the representation is like that. The representation is like this is the so this is the electron. Actually, it will donate one electron to the lattice. It will donate the one electron to the lattice, and the representation of the n-type semiconductor. It will donate one electron to the lattice, and this is the electron. Okay, the representation of n-type semiconductor. Okay, and another thing, if anyone asks like that, it will donate the electron, so it is the positively charged. No, that thing I am telling, no. Actually, the n-type semiconductor, it is the neutral semiconductor. Neutral. This question asked in the many examination, the written test. The neutral semiconductor means, uh, you can't, so don't confuse by the seeing of this the positive sign. It is the donor atom, of course this is the symbol, but this thing happen only inside the lattice. Okay, this thing happen inside the lattice. Okay, but overall if you observe the n-type semiconductor, so this is the lattice. Okay, so the inside the lattice, this is the positive charge, this is the positive charge, this is the positive charge electron, positive charge electron, positive charge electron. But anyone ask like that, the n-type semiconductor behaves as a insulator, so means this the positively charged, या negatively charged, या neutral, या none of these. So that time you need to tell this is the neutral. Because of that, overall it will behave as a neutral. Okay, this thing you should remember. Overall we will tell this is the neutral. Okay, inside the lattice it happens. So this is n-type semiconductor is the neutral semiconductor. Overall I am telling. Okay, and one thing, the constant I am telling, how you can calculate the means the minority carrier concentration, the whole concentration. Okay, for that purpose we have a one law is there, law of mass action. Law of mass action. Okay, this law what tells, according to the law of mass action, in any semiconductor bar, the product of the concentration of free electron and hole, it will be always the square of the intrinsic carrier concentration. Okay, it is the square of intrinsic. This is the intrinsic. It stands for the intrinsic. Okay, this thing, according to the law of mass action, the product of the free electron concentration and hole concentration is equal to the square of the intrinsic carrier concentration. Okay. On the basis of that, I am writing the whole. Actually, in case of the n-type semiconductor, in case of the n-type semiconductor, I told the majority carrier concentration is electron. Okay, that is the n is equal to donor majority carrier concentration. So how can you calculate the majority carrier concentration? P is equal to, so P is equal to Ni square. So Ni square n divided by Nd, yeah, n. Yeah, you can tell. This is the minority carrier concentration in case of the n-type semiconductor minority. I hope you understand. I am telling the basic idea about. You should remember only one thing. This is the representation of the n-type semiconductor, and this is the donor semiconductor. Okay, and overall it will be neutral. That thing happen inside the only the lattice. Okay, this thing I told. Now I am coming with the p-type semiconductor. P-type semiconductor I am telling on the brief. Otherwise video will be very lengthy. Okay. So this is the p-type semiconductor. Okay. This is the p-type. So in case of the p-type, we add the third group element. Okay. We add the third group element. So third group element is boron and aluminium. So this is the third group element, means only the three valence electron is there. Okay. So only three electron valence is there. So if we add the boron atom, one, only three valence electron is there. But we are doping in the intrinsic semiconductor. But intrinsic means silicon semiconductor have a four valence electron. This is the silicon, and one silicon atom left. Okay. So this is the covalent bond. Okay. So after all, one electron left. See, the one electron left. Okay. So at zero Kelvin, it behaves as an insulator. But if we increase the temperature, this covalent bond will be break and some electron will be free. Okay, electron will be free and it behaves as a conductor. So see, firstly I am saying, actually this electron is left. Okay, So it will absorb, so it will take one electron from the silicon. Actually there are so many, silicon is there, silicon is there, silicon is there, so it will take one electron and it will make our bond. But for that purpose, that's why I am telling, in case of the p type semiconductor, this is the acceptor atom. It will accept one electron and it will get the negatively charged, and this is the whole representation. So this is the representation of the p type semiconductor. Okay, so that's why in case of the p-type semiconductor, the majority carrier concentration is whole, that is the H, and that is the acceptor atom. I am telling, this is the acceptor atom. Okay, acceptor, acceptor atom. All the atom will be ionized and acceptor atom, and concentration is same, no problem. 10 to the power I think 13 like that. Okay, not much, 10 to 13, yeah, 10 to the power 14 per centimeter cube. This is the data, observed data. So in case of the p-type semiconductor, in case of the, so this is the H, don't confuse. Okay, sorry, actually I write N and P same like that. That's it. So this is the H symbol. Okay, this is the H. So this is the majority carrier concentration. So in case of majority, so majority carrier. So in case of the p-type semiconductor, whole is the whole will be the majority carrier concentration. Okay, majority, and electron will be the minority carrier concentration. This is the electron. So electron will be the minority carrier concentration. Okay, minority. So this is the minority carrier concentration. Okay now, so in case of the p-type semiconductor, hole will be majority and electron will be the minority semiconductor. How can you calculate? With the help of law of mass action. So this is the for sorry, this is not a n. Actually I need to like that, here I need to write the p. Okay now, sorry. Okay, so this is the whole representation p. P I think used already. Okay, so the P, that is the acceptor atom, the acceptor atom Na. Okay, with the help of law of mass action, how we can calculate the N, means the minority carrier concentration. Electron will be minority in case of the P type. So the N you can calculate like that, Ni square divided by Na. Okay, this way you can calculate. And overall this semiconductor will be a neutral. Okay, overall this semiconductor, overall it will be, overall it will be neutral. Okay, overall it will be neutral. See, so in case of the p type semiconductor, I drop the third group element. So one electron, this is the means less. That's why this is the acceptor atom. Okay, acceptor. In case of the p-type semiconductor, the whole is the majority carrier concentration, and electron will be minority carrier concentration. Okay, this is the whole for p representation. For p, I represent. Okay, and p, and how can calculate the electron? By the help of law of mass action. I hope you understand well. Okay, and this is overall the neutral semiconductor. Don't confuse by the seeing this of this. This is the negatively, yeah. Inside the lattice that open negatively charged. Inside the lattice there are the so many the negative charge is there. This is the negative hole, negative hole, negative hole, negative hole like that. But if we talk overall it behaves as a neutral. Okay, I think I told in the brief, in the very details about the intrinsic and extrinsic semiconductor. So before the go next, what thing you need to remember? Okay, only you need to remember like that, the n-type semiconductor, it is the donor semiconductor, you can tell, and in that the electron is the majority carrier concentration, and whole is the minority carrier concentration. Okay, that thing will be helpful only, and the representation of the n-type semiconductor is like that. It donate one electron and it will get the positively charged, and overall it will be neutral. Okay, and about the p-type semiconductor, What I told p type semiconductor, this is the acceptor atom. Here I dope means third group element I dope. So the in case of p type, majority carrier concentration is whole, and the minority carrier this is the majority carrier whole, and the minority carrier concentration is electron. So with the help of law of mass action, you can calculate this thing. I think video very lengthy or not. Oh yeah, this is very lengthy. So I'm stopping up to that, and in the next part I will discuss about the current and p n junction. Thank you.